So good morning, everyone. Today I'll take this lecture, and so before starting, what I can say is that in last lecture you all have learned about the definition of graphs, and then degree of a vertex, cycles, walks, paths, and all those. Today we will start with the basic theorem which related to the cycle and degree of vertex. So what it is that every undirected finite graph with vertex degree at least 2 has a cycle. Means if in your graph all the vertex has degree at least 2, then this graph must contain a cycle. If we look at the proof, suppose the order of the graph is p, means the number of vertices in the graph is p. And if possible, let G do not have any cycle. Now we start with an arbitrary edge, means choose two vertices V1, V2 which are adjacent. Okay. Now since now look at the vertex V2. Since degree of V2 is at least 2, there will be some other vertex say V3 which is not V1 and V2, but V2 is adjacent to V3. Means that here we have start with this edge initially, but since V2 has degree at least 2, so there will be another vertex V3 which is not in the which is neither V1 nor V2, but V2 is adjacent to V3. Means we have this path V1, V2 and V3. And again, since degree of V3 is at least 2, there will be another vertex say V4 which is not V3 and V2 which may be V1, but we will see it on later, such that V3 is adjacent to V4. Okay, now if V4 is same as V1, then we have a cycle, right? V1, V2, V3 and then again V1. But suppose V4 is not equal to V1. So in that case, this V4 will again have degree at least 3. Sorry, degree at least 2. So there will be another vertex which is adjacent to that V4. By proceeding in this way, we will see that there is a path V1, V2, V3 up to Vn plus 1. But since again here degree of Vn plus 1 is at least 2, so there will be another vertex say Vn plus 2 which is not in this collection, but Vn plus 1 is adjacent to Vn plus 2. Now, since our order of the vertex is p, so this path the length of this path can be at most p, and the end vertex should be vp. Now here again, degree of vp is p. Sorry, degree of vp is at least 2. So this vp must be adjacent to some other vertex. Means that we have this situation, this collection of vertices vp minus 2 and here again vp minus 1 and vp. Now degree of vp is at least 2 and vp is already adjacent to vp minus 1. And since degree of vp is at least 2, so vp must be adjacent to at least one of these vertices. And suppose it is vj. So if Vp is adjacent to Vj, so what we have is that we have this Vj plus 1 up to Vp path, and again Vp is adjacent to Vj, so we have the cycle. Means Vj plus 1 up to Vp and again Vj. So G must have a cycle. So is it clear?
Yes, sir.
Yes, no. You should response. Okay, otherwise I will not get whether you are getting or not. Okay, so if it is clear, we will move to the next portion, which is called the complete graph. Let's look at the definition. A complete graph is a simple and undirected graph in which every pair of distinct vertices is connected by a unique edge. Means that if you in your graph, if you take any two vertices from the graph, then you can find it, then there will be an edge. Means any pair of vertices is connected by a unique edge. We denote a complete graph with n vertices by kn, and it's easy to see that in any complete graph kn, it has nc2 or n into n minus 1 by 2 edges. Here is an example. You see that it's on complete graph on 5 vertices. It's k5, means here you have 5 vertices and all the vertices is adjacent to remaining 4 vertices. Here if you look at this vertex, then it is adjacent to this one, this one, this one and this one. If you look at this vertex, it is adjacent to this one, this one, this one and this one, and so on. Okay, so let's move to the here I want to make one comment that if you have a complete graph kn, then degree of each vertex is n minus 1. If you look at here the complete graph is k5 and degree of each vertex is 4. You see that 1, 2, 3, 4, and here for this vertex it's 4 also, and it's same for all the others. Next it is bipartite graph. What's the bipartite graph? A bipartite graph is a graph whose vertex set can be divided into two disjoint and independent sets, U and V. So here, first of all, here the vertex set is divided into two parts, U and V. It is fine. But what do we mean by independent? Independent means if you see any of the vertex sets U or V, then and if you take any two vertex from U or any two vertex from V, then there will be no edge between them. That's what called independent. Okay. So in a bipartite graph means your vertex set will be divided into two disjoint sets, or it is partitioned into two sets, U and V, which are independent, such that every edge connects a vertex in U to one in V. Means yes. So if you take any edge, you see that its one end is in U and other end is in V. These vertex sets U and V we call the parts of the graph, and we write a bipartite graph as usually we write it as UVE, where U and V are the partitions of the vertex set and E is the set of edges. We can make one comment also here that in a bipartite graph is a graph that does not contain any odd length cycles. So this can be a problem you can solve, or I think it is there in your tutorial sheet as well. Okay, so is it clear the definition of bipartite graph? If not, please tell me. If not, please tell me. I will explain once again. Okay, so if it is clear, now let's look at the complete bipartite graph. Earlier we have seen a complete graph means where any pair of vertices is connected by an edge, right? And here, what do you mean by complete bipartite graph? Can anyone tell me? What do you mean by complete here?
Sir, maybe it could be that every vertex in set U is connected to a vertex in set V.
Yes,
to each of the vertices in set V.
Yes, exactly. Means, in other words, if we say that if we take any vertex from U, say it is V1, and if we take any vertex from V, say it is V2, then V1 and V2 are adjacent in G. Right. So here is the definition that it is a bipartite graph. So, bipartite graph means a complete bipartite graph. First of all, it's a bipartite graph. So that is why its vertexes should be divided into two parts. So we will write it as V1, V2, E, such that every two vertices, so V1 belongs to capital V1 and small v2 belongs to capital V2, such that V1, V2 is an edge in E. Here also we say that a complete bipartite graph with partition size V1 is M, and if the order of V means if the cardinality of V1 is M and cardinality of V2 is N, then this complete graph is denoted by KMN, where M plus N is the order of the graph and M and N are actually the number of vertices in the partitions. Here also we M is greater than equal to N in general. We write it. We write the complete bipartite graph KMN in such a way that M is greater than equal to N. So here is an example K53 means in V or in U we have 5 vertices, and in the second partition we have 3 vertices, and you see that all the vertices in the first parts, all the red vertices are adjacent to all the blue vertices. If you look at this one, this vertex it's adjacent to it, this one, and this one, and similarly for the other vertices. Okay. So shall I move to the next part? It's clear?
Yes, sir.
Yes.
Sir.
Sure. Okay, so let's what's the degree sequence? So are you guys familiar with the degree? I hope so, because we have started today. We have started a theorem on the degree of vertex, right? So what is the degree? Degree means degree of vertex is the number of edges incident to that vertex, right? So and generally we denote it by digv or dv and sometimes dv, but digv is better to use. So now what is the degree sequence of a graph? In a graph G, if we write down the degrees of all the vertices in a non-increasing order, then we will find a finite sequence. So and this sequence will be called degree sequence corresponding to that graph. Okay, so if we look at this example, if we look at this graph here, we have this vertex, we have this one, and this one. So we have 3 vertices of degree 1. We have this vertex with degree 3, right? 1, 2, 3 means adjacent to this vertex is incident to 3 edges, so it has degree 3. And if we look at this vertex, it has degree 2. Similarly, this one has degree 2. So this one is a 2 degree vertex, and it is also 2 degree vertex. So in this graph, we have 1 3 degree vertex and 4 2 degree vertices and 3 1 degree vertices. So if we write down the degree sequence of this graph, it will be 3, 2, 2, 2, 2, and then 1, 1, 1. Means this one. 3, then 4 times 2, and then 3 times 1. It's a multi-set. You can say it's a multi-set actually. And similarly, if you look at this graph also have the degree sequence this one. So how? If you look at this vertex, it has degree 3, and there is only one vertex of degree 3, so 3 will come first, and there is no vertex of degree more than 3. If you look at these 4 vertices, this one, this one, this one, and this one, you see the degree of all those vertices is 2. So we will have 4 times 2 in the degree sequence, means 2, 2, 2, and 2. And we have 3 vertices of degree 1. So there will be 3 times 1. Okay, so is it clear? Yes,
Yes, sir.
The next part, graphic. Now next is a graphic sequence. So here here we have seen the degree of a graphs and degree sequences. So now you see that you can take any such collection of numbers, right? Any such non-increasing collection of numbers. So and you may ask whether this collection or this sequence will form a degree sequence of some graph or not. And That is our next definition, that a sequence which is the degree sequence of some graph is called graphic. Means if you take an arbitrary non-increasing sequence of numbers, or sequence of positive natural or positive integers, or sequence of natural numbers, and if there is some graph which has the degree sequence as your taken sequence, then this sequence will be called graphic or graphical. If you look at see a definition, a sequence is a degree sequence of some graph, that is for which the degree sequence problem has a solution, is called a graphic or graphical sequence. So if we see this example, means 3 and 2, 2, 2, 2, and then 1, 1, 1, means 3 and then 4 times 2 and 3 times 1. Then we see earlier that this graph has degree sequence this one. Means this graph has degree sequence this one. Therefore, this sequence is graphic. If we look at this one, 3, 3, 1, it is not graphic. So why it is not graphic? 3, 3, 1.
Sir, we can't. There does not exist a graph that will have such a sequence, because if there are 3 vertices only and 2 of them have 3 edges, then the third one must also have. It must have at least. I mean, for it to have 3 edges, then it would have to have like a self loop as well, right? So the first one must have at least 2. Sorry, like it should be 3, 3, 2. That might exist, but 3, 3, 1 does not.
Yes. There is a simple result called handshaking lemma, right? What is handshaking lemma?
That the summation of degrees should be even.
Yes. So here, what is the summation here?
It's 7. So that's
yes, so it's not possible, right? Okay, so that is
exactly.
why
That is also fine, because it is just a simple one that first graph has only 3 degree 3. That is not possible because we have only exactly 3 vertices.
Yes.
So simple graph is not possible.
Yes. So let's move to the next degree, means 5, 4, 4, 3, 3, 2. So whether, can you please tell me whether it is a graphic sequence or not? What about this one?
No, so sir. Using the corollary that we did in last class, that there must exist even number of odd degree vertices.
Yes. So there must have even number of odd degree vertices. Here also, if you take the summation, it will be okay. It's fine. Even number of odd degree vertices.
If you take the summation, then it will be odd. So this
yes.
is again the contradiction.
Again, not possible. Okay, so let's move to the next part. Means show that a theorem is a degree sequence with all degree elements with all distinct elements cannot represent a simple non-directed graph. Means suppose you have a graph with n vertices, and so if you take a degree sequence, then see, if you have a graph with n vertices, then your degree sequence must contain n element, right? Means the degree of all the vertices. So since there are n vertices, so there should be n degrees. Now here this theorem states that degree sequence, if this theorem says that these degrees in your sequence cannot all be different. Means degree sequence with all distinct elements cannot represent a simple non-directed graph. So if we look at the proof, suppose your vertex set is v1, v2 up to vn. Now here we see that none of the vertices is of degree n, because we have taken a simple graph, means loops are not allowed. Okay, so none of the vertices have degree n, because if we have if v1 has degree n, then v1 must be adjacent to n other vertices. Okay, but in your graph you have only n vertices, so except v1 we have exactly n minus 1 vertices. So degree of some vertex, so some vertex of degree n is not possible. So only possible degree sequence is 0, 1, 2 up to n minus 1. Now again, if there is a vertex of degree n minus 1, then this vertex must be adjacent to all the remaining vertices, means all the remaining n minus 1 vertices. So here so we cannot have a vertex without an incident edge, means we cannot have an isolated vertex, because all the vertices should be adjacent to the vertex of degree n minus 1, and therefore vertex with degree 0 is not possible. So this degree sequence is also not possible. So, and this proves our result, right? Means that in a simple and non-directed graph, there cannot be a degree sequence with all the distinct elements. Okay, so is it clear?
Yes, sir.
Okay, so next we see an important result called Havel-Hakimi theorem to prove whether a degree sequence, whether a given non-increasing sequence is a degree sequence of some graph or not. So what is the statement? It states that A is equal to, if we take this sequence, say S, T1, T2 up to TL, T1, T2 up to Tn is graphic, means this sequence A is a degree sequence of some graph if and only if the sequence A dash, if we take the sequence A dash as T1 minus 1, T2 minus 1 up to Ts minus 1, comma D1, D2 up to Dn. So this sequence means A dash is graphic, means your first A sequence is graphic, means there is some graph with degree sequence A if and only if A dash is graphic, means there is some graph with degree sequence A dash. Here you can have some confusion here, that we have taken first S and then T1, T2 up to Ts, and here we are taking summation up to Ts. Whether this summation becomes negative or not, it is not possible, because we have taken S here. So your first vertex has degree S, so there must be at least S vertices with positive degree. So and those S vertices can be T1 up to Ts if all the remaining vertex has degree 0. Okay, so this A and A dash both are consistent sequence, or both exists, first of all. Okay, so now let's look at the proof. So first we prove the backward one, means if A dash is graphic, then A is graphic. So suppose A dash is graphic, so then what we can say is that by definition there is a simple graph G dash with the degree sequence A dash, means where A dash is the T1 minus 1 and so on and so forth, Ts minus 1 and then D1, D2 up to Dn. Now if we add one extra vertex V which is not in G dash, and then add the edges with the vertices of degree T1 minus 1, T2 minus 1 and Ts minus 1, then we see that this vertex V has degree S, because it is adjacent to S distinct vertices. And again, since the first S vertices T1 with degree T1 minus 1, T2 minus 1 and Ts minus 1 are adjacent to the new vertex V, so their degree also increased by 1. So we have a degree sequence as S, comma T1, T2 up to Ts, and then D1, D2 up to Dn. So which is graphic. Therefore, A dash is graphic implies A is graphic. So we have proved the backward direction. Now let's look at the forward direction. Okay. So assume that the sequence A, means this sequence S, T1, T2 up to Ts and D1, D2 up to Dn is graphic. So then by definition what we can say is that there exists a simple graph G with the degree sequence A. Okay, and let us take the vertices of this G of this graph G as S, T1, T2 up to Ts and D1, D2 up to Dn. Right? So here T1 means the degree vertex with degree T1, or Ti means vertex with degree Ti. And here again I have taken this vertex D1 with degree D1, small d1. Okay, so now here we observe that we do not know the vertex with degree S is adjacent to the first S vertices, means T1, T2 up to Ts or not. Okay, so that is why we cannot remove S initially to get such sequence, means T1 minus 1, T2 minus 1 up to Ts minus 1 and D1, D2 up to Dn. So we break this into two cases. In first case, suppose this S is adjacent to first S vertices T1, T2 up to Ts. Then then what happens if we remove this vertex S? So then if we remove this vertex S, we will left with a graph G dash with vertices T1, T2 up to Ts and D1, D2 up to Dn, but where degree of this T1 will be small t1 minus 1, degree of T2 will be small t2 minus 1, and so on and so forth. Degree of Ts will be small ts minus 1, and the degree of remaining vertices are same. So we have a graph with degree sequence A dash, right? So A dash is graphic. But if S is not adjacent to some vertex Ti, for some, I mean, suppose if S is not adjacent to some of the vertex in this list, means T1 to Ts, then what happens? Then what we will do is that we will apply some operations on the graph, means we will remove some of the edges and then again attach some of the edges to get another graph, say G double dash, where this vertex S is adjacent to the first vertices, but this G double dash has the same degree sequence as A. So how? So how do we get such graph? So we see that here our vertex S has degree S. So this S vertex must be adjacent, and since this S is not adjacent to some of the vertices present here, so and S has degrees of small s, so S must be adjacent to some vertex of some vertex in the list D1, D2 up to Dn. So is it clear? Are you getting my point or nothing?
Yes, sir.
See here, degree of S is small s, okay, and here we have S vertices in the list from in T1, T2 up to Ts, but this S is not adjacent to some of the vertices, and since S has degree S, so S must be adjacent to some of the vertices in the list in D1, D2 up to Dn. That's it. So let the degree, suppose S is adjacent to Dj, okay, and let the degree of Dj be Dj, and which we have assumed earlier that degree of his Di is a small di. Now we then what we know from the degree sequence is that, what do you know from the degree sequence? The degree sequence is always in non-increasing order, means this Ti since it is a degree sequence, so this Ti are always greater than equal to Dj. Right, means these terms are always greater than equal to these terms. So we have two possibilities, either Ty equal to Dj or Ti greater than Dj. Means some of the Ti means some of this Ti, or say it is Ts and this D1 are same, or Ts is strictly greater than this D1. So this kind of cases may happen. So now consider the case where Ti equal to Dj. So let's look at the picture here again. Okay. So here we have the degree sequence. This 3, 2, 2, 2 and 1 means 4 times 2 and 1. Here again we have this S has degree 3 and 3 vertices T1, T2 and T3 have degree 2. and again D1, D2 has degree, D1 has degree 2 and D2 has degree 1. Now now we are trying to find out a graph G dash where this vertex S is adjacent to T1, T2 and T3 only. But because but in our original graph S is adjacent to D1, but we want such a graph where this S is adjacent to T1, T2 and T3. And after getting such graph, we just simply remove the we just simply remove the vertex S and corresponding edges. Then and we will have a graph with vertices T1, T2, T3 and D1, D2, where the degree sequence will be T1 minus 1, T2 minus 1, T3 minus 1 and then D1, D2. Okay. So what do we do here? We remove this. What do we do here? We just simply switch the vertices D1 and T2. So if just rename this vertex as T2 and this vertex as D1, we get such a graph, right? Is it clear?
Yes, sir.
See, if this degree of this D1 and degree of this T2 are same, but and here S is adjacent to D1, but S is not adjacent to T2. So now we take such a graph where S is adjacent to T2. We just rename this vertex as T2 and this vertex as D1. So we have such a graph where H is adjacent to T2 and T1 and T3, but H is not adjacent to D1 and D2. So here is the result, means here is the graph. Okay, so we have a graph where S is adjacent to T1, T2 and T3, or S is adjacent to T1, T2. Here in general, a graph S is adjacent to T1, D2 up to Ts, but not adjacent to D1, D2 up to Dn. In case 2, sorry, if now earlier we had Ti equal to Dj. But if Ti is strictly greater than Dj, what happens if Ti is greater than Dj? Again, let's look at the picture. So here we have this S. Okay, and this S is adjacent to D1 as earlier because S is not adjacent to some vertex, say T2. Now, and what is the case is that Ti is greater than Dj, means degree of the vertex which is not adjacent to S is greater than equal to is strictly greater than the degree of the vertex which is adjacent to S. So here is the case is that this T2 is not adjacent to S, but degree of the vertex T2 is 2 and S is adjacent to D1, but degree of D1 is 1. So what do we handle? How do we handle such cases to get a graph with the same degree sequence but S is adjacent to T1, T2, T3? We just simply remove the edges, this S D1 and T2, T3. Here also I would like to make one point is that since Ti is strictly greater than Dj and Ti is adjacent to more vertices than Dj, because the number of vertices Dj which are adjacent, the number of vertices which are adjacent to the graph vertex Dj is less than the number of vertices which are adjacent to the vertex Ti, because Ti has greater degree than Dj. So therefore there must be another vertex W which is adjacent to Ti but not adjacent to Dj, right? Because here Ti is strictly greater than Dj. So now, so same case we have here, that this T2 has degree 2 and D1 has degree 1, and so there must be one vertex which is adjacent to T2 but not adjacent to D1. So here it is T3, because T2 is not adjacent to S anyway. So here we have taken the vertex T3, so T2 is adjacent to T3, but T3 and D1 are not adjacent. Now we remove the edge T2, T3 and S D1. We have removed these two edges and add the edges S T2 and T3 D1. So we get this graph here, and if we look at the degree sequence of this graph, it has S vertex has degree 3, T1 has degree 2, T2 has degree 2, T3 has degree 2, D1 has degree 1, and D2 has degree 0. So the degree sequence of this graph is 3, 2, 2, 2, 1, 0. So similarly here what we do is that we removing the edges S, dj. Here this one is our S, dj, and remove Ti, W, means the vertex which was adjacent to our the vertex which is not adjacent to S, and then attach and then add the edges S, Ti. Add this we will add this edge S, Ti, and add W, dj, means this was on our W, so we add this edge. Okay, and so we get that S is connected to is adjacent to the vertex Ti. So in this way, so which vertex in this way, the vertices which are not adjacent to Ti, we can apply the same procedure to get a graph where S is adjacent to all Ti's. Okay, so finally we have a graph, say G double dash or say G1, where which has degree sequence same as this A, but the first vertex with degree S is adjacent to the vertices with degree T1, T2 up to Ts. So we have the same situation as case 1. So S is adjacent to the vertices T1 up to Ts. So we just simply remove the vertex S. So we will get a graph with degree sequence T1 minus 1, T2 minus 1, and so on and so forth, Ts minus 1, then D1, D2 up to Dn. So that is graphic. And hence we have proved the result in both directions. So tell me if you have any problem in this proof. I think you will have some problems. So please tell me if it is not clear, or if you want any more. Anyone? Is it clear to you?
Yes, sir, it is clear.
Okay, so if it is clear, then fine. If it's not, please tell me. Okay, so if it is clear, then I shall move to the next portion. If it's not, please tell me. I will explain once again, because we have enough time to explain. Okay, so if not, I shall move to the next portion. So some examples. So you have given one degree sequence, and you have to tell whether this degree sequence is graphic, and we will apply the Havel-Hakimi theorem here. So so at first step, what we do is that we so this degree sequence is graphic by Havel-Hakimi theorem if and only if this 3 minus 1, 3 minus 1, 3 minus 1, 3 minus 1, then 2 minus 1, 2 minus 1, 2, 2, 1, 1 degrees graphic, right? Means this is graphic if we remove the vertex with highest degree 6, we will get the degree sequence as 2, 2, 2, 2, then 1, 1, 2, 2, 1, 1. So this is graphic. Okay. So now we will rearrange this degree sequence in a non-increasing order. So what we will get is that we get this degree sequence as this one. So now again we apply the Havel-Hakimi theorem. So your first vertex has degree 2. So if we repeat the process, means if we remove this vertex, then we will have a graph with degree sequence 1, 1, means we will so this will be 2 minus 1, then 2 minus 1, then and the remaining others will be same, right? So it will be 1, 1, 2, 2, 2, and then 1, 1, 1, 1. and if we rearrange these terms, we will get 3 times 2 and then 1 1 1 1 1 1. Okay, so again we will apply the Havel-Hakimi theorem that this degree sequence is graphic if and only if and only if the degree sequence 2 minus 1 2 minus 1 1 1 1 1 1 1 is graphics, and means this degree sequence is 1 1 1 1 1 1 1 1 is graphic. And you see that you can easily see that this is a graph. This is a you can see that we have 8 vertices here, right? And all the vertices has degree 1. So you can see that it should have 4 edges, and all the 4 edges are adjacent to, means there will be, and each pair will be adjacent by each vertex will be adjacent to each vertex will incident to exactly one edge, and since one edge has 2 ends, means one edge is incident to 2 vertices, so we have 4 edges, and so if we remove all the edges, we will get all the vertices as isolated vertices. So this sequence is graphic, and therefore by Havel-Hakimi theorem, this sequence is graphic, and so on and so forth. This sequence is graphic. So is it clear? Means you just take this degree sequence and then keep doing applying the Havel-Hakimi theorem. At first step, you have this sequence, means 3 minus 1, 3 minus 1, 3 minus 1, 3 minus 1, and again 2 minus 1, 2 minus 1. So you will get this sequence, and then rearrange this degree sequence in a non-increasing order. Again apply Havel-Hakimi theorem here, you will get the degree sequence as this one. So if we again rearrange, you will get the degree sequence this one, and again apply Havel-Hakimi theorem, you will get the degree sequence as this. So this is graphical if and only this is graphical. This is graphic if and only this is graphic, and this is graphic if and only this is graphic. So that's all. And therefore, since we have a graph, means since this sequence is graphic, we have our original sequence is graphic. Okay, so is it clear? I shall move to the next problem. So tell me, is the sequence is the sequence 6 5 5 4 3 2 1 is graphic? So again we shall apply the Havel-Hakimi theorem. At first step, we shall remove the vertex of degree 6, right? So what we will get is that by Havel-Hakimi theorem, this is graphic if and only if 5 minus 1, 5 minus 1, 4 minus 1, 3 minus 1, 2 minus 1, and 1 minus 1 is graphic, because it is first vertex has degree 6 and we have 7 vertices here. So this is graphic if and only for the degree, if and only the sequence 4 4 3 2 1 0 is graphic. Now again we remove one of degree 4. Okay, so if we again apply Havel-Hakimi theorem, so this sequence is graphic if and only if 4 minus 1, 3 minus 1, 2 minus 1, 1 minus 1, and 0 is graphic, means 3 2 1 0 0 is graphic. Okay. So now if we look at this degree sequence, here we have one vertex of degree 3. So this vertex must be adjacent to 3 other vertices. So means that in this degree sequence, there must be 3 vertices with non-zero degree. But it is not the case because we have only 2 vertices with degree non-zero. So this is not graphical, right? Means 3 2 1 0 0 is not graphical, and therefore if I have Havel-Hakimi theorem, the earlier graph is not graphical, means this degree sequence is not graphical, and therefore this degree sequence is not graphic or graphical. Okay, so we have seen by Havel-Hakimi theorem, we have proved that this degree sequence is graphic, and by example that this degree sequence is not graphic. It is not graphic. Okay, so we have both the examples. So is it clear?
Sir, we could simply apply the handshaking lemma also here, because they're 5 5 3, so there are 3 odd vertices, 3 vertices.
No. Here you see that 5 5 3 2 1 also there, no?
Oh, okay. Sorry.
Yes. See, once you are given a degree sequence, you first check that whether the the number of odd degree vertices or is even or not. So if it is not even, then you just simply say you have a conclusion that this cannot be a degree sequence of some graph. But if it is but if there are 4 vertices, it means if there are even number of odd degree vertices, then this can be a degree sequence of some graph. In that case, you have to apply Haber-Hakami theorem. Okay. So is it clear? Means these 2 examples.
Yes, sir.
Those are very important, right? So okay, so that's all I can say. If it's clear, I will move to the next next thing, means regular graph. So a graph G is said to be regular if each vertex has the same number of neighbors, means degree of all the vertices is same. So if we have such a graph and degree of if we have a regular graph G and the degree of all the vertices is the number R, then we call the graph as an R regular graph. Okay, so it means this R regular. Okay, so we'll use some notations that for a graph G, by capital delta G, it's the maximum of DV, means maximum degree of vertices. Okay, means capital delta G is maximum degree of vertices and small delta G is minimum of degree of vertices present in G. Okay, so here is a note that if this maximum means if delta is capital delta G and small delta G are same, then the minimum degree and maximum degree are same. So all the vertex should have the equal degrees, and it is capital delta G or small delta G. So the graph is regular. Okay. So what we have learned that by capital delta G we mean the maximum of degree of the vertices present in the graph, and small delta G is the minimum of the degrees of the vertices present in the graph. Okay. So in exam and in other cases also, if there is nothing mentioned and just simply written as capital delta G or small delta G, then you should understand that by capital delta G, it means it's the maximum of the degrees of the vertices, and by small delta G, it means minimum of the degree of the vertices. Okay. If anything is not mentioned there. So now next, it's the last result of this lecture, that every graph is an induced subgraph of an R regular graph. So what is an R regular graph? An R regular graph is a graph where each vertex has degree R. Okay. So now let's look at the proof.
Sir,
so yes.
Sir, what is the induced subgraph?
Induced
Subgraph.
Yes. So suppose you have a graph G V comma E. Okay. Now you take a subset of the vertex set. Say suppose U be a subset of the vertex. It can be either proper subset or improper. Means it's non-empty. Okay. So now you have some vertices in your set U. Now take a pair of vertices. Say U1,
just
U2
just
from
a
U.
minute. So informally, you can just say that suppose you have a graph. Now, if you delete some vertices or some edges, then you will get a subgraph. That is called the induced subgraph.
So induced subgraph and subgraph are same, sir.
Right. Yeah.
Okay, sir.
It's a subgraph with some other properties. Means if you take two vertices from the set, means U, then means if you take two vertices and these two vertices are adjacent there, if and only if it is adjacent in your original graph. That's it.
Okay, sir. Thank you.
Okay, so it's every graph is induced subgraph of some R regular graph. So take R to be this delta G here. This delta G means the maximum of the degree of vertices, and we will use the induction of this delta G minus small delta G, means the maximum degree and the minimum degree. So now you see that if this difference is 0, means if maximum degree is equal to minimum degree, then this graph is already irregular, right? But if it is positive, means if the difference is positive, means then so there will be some vertex with degree less than this delta g, and that's it. Means there will be some vertex which has degree different from this r, or different from this capital delta G. So in this case, what we will do is that we will take two different copies of the original graph G, say G1 and G2. So now we have two copies of G, means G1 and G2, and for every vertex V which is not adjust, which has degree strictly less than this R, or means strictly less than the maximum degree, we take two copies of the vertices, say V1 and V2, from G1 and G2. So means that I'm saying once again, we will take two copies of the graph G, say G1 and G2, and for each vertex which has degree strictly less than capital G, we will take two copies of that vertices as V1 or V2 in G1 and G2 respectively. Means V1 and V2 are actually the copies of this vertex V in G1 and G2. And for all such vertices V1 and V2, we just simply add the edge V1 V2. Means we create a new graph G dash where the vertex set is VG1 union VG2 and S set is S set of G1, S set of G2 with extra edges are V1 V2, where these V1 and V2 are actually the same the copies of the same vertex V, same vertex V, where V has degree strictly less than delta. Okay, so is it clear? Which extra edges we are taking here to construct G dash? Means,
So please explain once more.
yes, where degrees are smaller and we take two copies, one in G1 and other in G2, and they simply attach these two vertices by an edge. Okay. So then we will have a graph G dash, and you see that here all the vertices, we say if we take V1, then V1 has degree in G it has some degree, say it is S, but in G dash it has degree S plus 1, right? Because it is adjacent to the copy of the same vertex which was in G. So this difference R minus delta G dash is decreased by 1, means it is now R minus delta G minus 1. Now we see that if this is 0, then we are done. Means this G dash will be a regular graph, will be an R regular graph. But if it is not 0, then we apply the same thing here, which we applied for G. We apply the same thing for G dash as well, and to get some other graph G double dash, where R minus delta G double dash is same as R minus delta G dash minus 1. Okay, or simply R minus delta G minus 2. So proceeding in this way, after a finite number of steps, we will get a graph where delta G minus, means capital delta G minus small delta G is 0. Means, and this is, and capital delta G minus small delta G means is R minus delta G, and R minus delta G is 0 means all the vertex has the same degree. So we have a R regular graph. Okay. So now how do we get the induced subgraph? So see, here if we look at G dash here, if you look at G dash here, and if you take the vertices which was in G1, right? So if you look at the G dash and if we look at these vertices, and now if we consider the induced subgraph on G1, means on VG1, you can see that this is same as the graph G1, right? So, and G1 is nothing but the G. So G has a copy in G dash. Okay, and similarly G dash will have a copy in G double dash, and so on, so forth. So finally we have this graph G has a copy in the final graph as well. So our main graph G is a subgraph of is an induced subgraph of an irregular graph. So is it clear?
So
If it
what
is
does
not,
disjoint copies mean?
yeah, here
Yes, sir.
actually you have one graph means a G. You take two copies of it.
Okay. So then
Yes.
why are we calling them disjoint copies? I mean, and what is the difference like G1, G2?
Actually
Just
when
it
we are
is
taking
just you take two copies of G.
Yes, sir.
That's all. Just take two copies of G. First take two copies of G, draw it, and then put some edges like given in this proof.
Okay. So the disjoint here does not have any significance.
No,
Okay, sir.
in that sense, no. Yeah, you are just copies. Disjoint means you take there is first take G1 and G2, okay, and there is no edges between G1 and G2. That's all.
Okay, sir. Got it.
And then there is no common vertex between G1 and G2. And for the induced subgraph, I just missed one point as Saurabh told here. So induced subgraph means it has one extra property. So that's mean it has a induced on vertices. For an example, suppose you have the graph say G is just a two edges, okay? G is just contains two edges with one common vertex. Okay.
Okay.
Now can you tell me what is the G tilde here? That is the regular graph. So you have three vertices and two edges, okay? You have just a path. Then what? This is your G.
So
now one vertex has degree 1, another vertex has degree 2, another vertex has degree 1. Right?
we'll
Now
draw the
what?
edge.
Yeah.
So the one edge between the 1 degree vertices.
Right. No. If you draw that, if you draw an edge between 1 degree vertices, then you will get a regular graph. But
Yes.
in that case, G is not an induced subgraph. Did you get my point?
So sir,
In that,
induced subgraph exactly what will be there like?
induced subgraph means it is induced on the vertices. So that's mean when you say that induced subgraph, say G is a graph and H is a induced subgraph. Now if you take that vertices of H, okay, vertices of H. Now if those vertices have an edge in the main graph in G, then that vertices should share an edge in H as well.
Okay, sir. Got it.
Okay. So for an example, if you take that the path of with three vertices and two edges, okay, then one vertex is degree 1, one vertex is degree 2, another vertex is degree 1. Now if you join the diagonal, that's mean if you made a triangle, then you will have a regular graph. That is fine, and your G is a subgraph of G tilde. That is fine, but that is not an induced subgraph.
Okay. I mean, we should have that edge. We should have those edges which are there.
Right, right.
Okay.
So what we will do to get a induced subgraph, we will take another copy first, and then we will join those 1 degree edges. So therefore now we will get a 2 plus 2 plus 2. We will get a 6 cycle.
Got it, sir.
Okay.
Yes.
Okay. Anyway, I will add the definition of induced subgraph. Okay. So is there any other question throughout the lecture? And it is really nice presentation, Saurabh.
Thank you, sir.
Yeah, students, please ask if you have any doubt, any questions. So we are here. We together will clear your doubt. We have half an hour. Okay, if there is no other questions, we can stop, I think.
Yes, sir.